Okay, okay. Quite a small audience today. Now, I don't know how much you've been paying attention to what's been going on all around the world about the coronavirus. And one thing I've been paying particular attention to is how universities have been responding. So you may have heard that some, such as my graduate alma mater, Stanford, have very abruptly required all classes to shift to being offered online. So this kind of class, not meeting. Tests having to be made take home, etc. Mostly places that have been hardest hit by the virus, but not necessarily. Last I checked, Mississippi does not have any confirmed cases, but even in a state that has very few, Ohio, those universities are also taking those kind of drastic measures. And bringing this up because it's a possibility that I am planning for. If all of a sudden I have to make this class and my other class shift to being offered without in-person class meetings, and just becoming an online class overnight, we all should be prepared for that possibility of some edict coming down from above that this has to happen for the remainder of the semester. So I don't want anyone thinking that just because Mississippi is one of the, I think, 12 states that have yet to have a confirmed case, that we're not going to see the same kind of disruptions that are happening elsewhere. So, and you can check the news to see what's being done elsewhere. The responses vary. I had a bunch of conferences lined up, planning to attend. One by one, they're all getting canceled or rescheduled several months in the future. So it's going to be a pain in the butt. And I think the sooner we all accept that frame of mind, I found it actually becomes easier to face whatever actually comes. So, university is still basically coming up with their response plan. They put out some information to us, but nothing that really calls for immediate action. Basically, what to do in case USM actually does have someone, student or faculty member or staff member, actually come down with the virus, which hasn't happened yet. So, we'll see. It's going to be a rough ride, but I'll do what I can for this class to try to have things go as smoothly as possible. Okay. Now, what's the theme for this week? It's all about non-homogeneous linear second-order differential equations. We saw one method for solving those on Monday, and now we'll see the other method. So, and then after I show you this method, then I'll do some more examples of both, because I didn't get to do everything that I had planned on Monday. Okay, so this is, I thought this was a working marker, and apparently I'm to be disappointed. Okay. Variation of parameters is an alternative to method of undetermined coefficients for solving these kinds of equations. So once again, we're trying to solve this kind of second order equation, possibly with initial conditions, where we have some non-zero function on the right side. And very important, in front of y double prime, I don't want to say no coefficient. Coefficient must be equal to 1. So I am going to give you a solution formula. It depends on that. So if you're given an equation that's not in this form, divide both sides so that whatever's in front of y double prime is just 1. Okay, and then you have whatever PUT and QT. So what is the method of variation of parameters? First, you do the same thing as for method of undetermined coefficients. You solve the homogeneous equation. So that'd be y double prime plus p of t y prime plus q of t y is equal to 0. And that will give you a fundamental set of solutions. So y1 of t, y2 of t. So this is where you get the roots of the characteristic equation. Based on those roots, real or complex or repeating, you come up with your functions, your exponential, sines, cosines, what have you. Now, if you are a constant, was what was covered last week, you're able to actually come up with these. If p and q are not constant, you don't really have any y1 and y2, but they may be given to you, and then you can proceed with the rest of the method from there. So the point is, one way or another, you have a y1 and y2. So you have your homogeneous solution that is just some linear combination of y1 and y2, where c1 and c2 are influenced by the initial conditions. Okay, so far there's nothing different. Now we'll see what actual variation of parameters is. Because in undetermined coefficients, you have to find a form for a particular solution based on what you're given for g of t. Not so this time. Here we assume that the particular solution that I've been calling yp of t. So really, this is another method of finding a particular solution besides undetermined coefficients. So we assume it has this form. It's similar to this. It's a combination of y1 and y2. The difference is what we multiply them by are not constants. So we have a function, w1 of t times y1 plus w2 of t, y2. And these functions, w1 and w2, those are your unknowns. So this is what we have to go find. And once we have them, then we can construct a particular solution. Now, here you can see where the method variation of parameters gets its name, because in the homogeneous solution, we have these parameters, C1 and C2. These are constants. Now we're letting those constants or parameters, so because this gives us a two-parameter family of solutions, what are we doing here? We are allowing the parameters to vary with time. So variation of parameters. Okay. So if you were to take this form of a particular solution and substitute it in here, then what do you end up with, and I won't go through all the details now, but they're in my notes, so it's not something you would need for a homework or test. What you end up with are a system of linear equations for the derivatives. So you get linear equations for w1 prime and w2 prime, and then you can integrate those to get w1 and w2. So what I'll do is jump directly to the formulas that you get for w1 and w2. So w1 of t is an integral of minus, don't forget the minus, y2 of t times g of t over the Wronskian, and I will define that momentarily, of y1 and y2. All right, so that's w1. And then w2 is similar. So again, you have an integral. Again, you have this Wronskian in the denominator. But what you have up top is no minus. It's y1 of t, and then you still have g of t. So remember, only w1 gets the minus. And for each one, if you're finding w1 or w2, it's the opposite y that goes in the numerator. This comes from the solution formula for 2x2 system of linear equations. The Wronskian of y1, y2, and I'm going to write here in parentheses a t, just to emphasize that the Wronskian is a function of t. It's generally not a constant. Well, sometimes it is, but don't assume it is. So this Wronskian is the determinant of a 2x2 matrix that has y1 and y2 in the first row, and then their derivatives, first derivatives, in the second row. Now the determinant of a 2x2 matrix. So we have y1, y2 prime minus y2, y1 prime. And so that's what goes in the denominator. So notice in each term, only one of a function, exactly one of the functions is differentiated, and you have a minus in between, not a plus. Okay. So that's it. That's the method of variation of parameters. That you solve a homogeneous problem first to get your y1 and y2. You work out these integrals, and I want to emphasize when you're working a problem, and you'll see this in the examples that I'll do, when you set up these integrals, before you work them out, simplify as much as you can. There's always opportunities to simplify the integrand first. A lot of things tend to cancel. It's just the way these problems tend to work out. So keep that in mind to save yourself some time later. So once you have W1 and W2, if that's where the real work is involved, so then the general solution of the original problem is y of t is constant times y1 plus another constant times y2. So this is your homogeneous solution plus w1 y1 plus w2 y2. So this is your particular solution. So adding the two together describes all possible solutions of this equation. And if you're given initial conditions, then you go ahead and find C1 and C2. The other comment I'll make is don't worry about a plus C, which sounds kind of odd, but here's why. Suppose instead of W1, I have W1 plus C. Well, then I'd have a constant times Y1. I already have an arbitrary constant times Y1. So adding a plus C would be redundant. It gives you more things to solve for than you need. You only have two initial conditions, and you already have two parameters to find. So you don't need to include a plus C. All right. Now, on a test, these formulas would be given. Questions at this point? All right. So I have one example from Monday that was undetermined coefficients that I didn't get to. So what I'm going to do is I'm going to solve the problem using both methods. Okay. Right, this will be initial value problem. So y double prime plus 4y is equal to t squared plus 3e to the t. Initial conditions, y0 is 0, y prime of 0 is 2. Okay. So this first part will be useful for both methods. So we solve the homogeneous problem, y double prime plus 4y is equal to 0. Okay. I'll check something here. Oh, actually, this particular homogeneous problem came up in the last example on Monday. So your characteristic equation is r squared plus 4 is equal to 0. There's no y prime term so in the equation, so there's no r term in the characteristic equation. So we saw on Monday that the two roots we get are complex. So there's no real part. There's an imaginary part of plus or minus 2. Therefore, our homogeneous solutions are cosine of 2t. And then we have sine of 2t. And we have a homogeneous solution. So that'll be part of our general solution at the very end. C1 cosine 2t plus C2 sine of 2t. Okay. Now, our g of t, the right-hand side, has two terms in it. Now, whenever you're doing undetermined coefficients or variation of parameters, what you're allowed to do is consider each term separately. Find a particular solution for a case of t squared, find a particular solution for 3e to the t, and then you can just add them together. Okay. All right, so we have, so I'll have step 2a here. So I'm going to let g1 of t equal the first term, t squared. Okay. So what we need, now in this case, I'm going to begin with undetermined coefficients for Monday, and then show the process again for variation of parameters. Okay, so in this case, we need the form of a particular solution. So what we have here is a polynomial of degree 2. That's t squared. There's no exponential, there's no sine, there's no cosine. So what we can conclude from that is that the particular solution is also going to be a polynomial. So we have some power of t times an unknown polynomial of degree 2, same degree as this. So that would be a2t squared plus a1t plus a0. S is the number of times 0, because it's a polynomial. 0 is a root of the characteristic equation. Well, look at the roots of the characteristic equation. So we're comparing 0 against these roots. All right, so this is what has to be done every single time undetermined coefficients. If you have a polynomial, you're checking 0. If you have an exponential, like e to the at, you're checking whatever a is. If you have like e to the at cosine or sine bt, you're checking a plus bi. You're checking against these roots that you got from the homogeneous problem. In this case, 0 is not one of the roots, so s is equal to 0. So that means we're not going to have this factor included after all. So the form of a particular solution is just going to be some second degree polynomial. Questions about this part? All right, this is the key part of undetermined coefficients, making sure you have the right form before you go ahead and do all the nasty algebra. So in this case, we're going to have 3 parameters defined altogether. Okay, so our particular solution, I'm going to put a superscript of 1 here because it corresponds to the first term in the right-hand side, the t squared. Actually, I'm not going to put it there because you'll think that's prime. So I'll put it down here. So that's just some second degree polynomial. Then, now I'm taking a derivative. So you need the first and second derivatives of this. So that'd be 2a2t plus a1. And then the second derivative. So that would be just 2a2. So all of this gets substituted into the non-homogeneous equation. So y double prime plus 4y is equal to t squared. So we're only looking at t squared right now. We'll get to the 3e to the t part later. So let's see what we get. So y double prime would be a2t squared plus a1t plus a0. No, totally wrong. Second derivative, 2a2 plus 4 times particular solution, 4a2t squared plus a1t plus a0. And that is equal to t squared. Okay. Now, what you do is you group by the powers of t. Okay. So, because they have to match terms involving those same powers of t on the right side. So we have 4a2 t squared. And then we have 4a1 times t. But the constant term is 2a2 plus 4a0. And that has to equal t squared. So now you match up powers of t on the left side with powers of t on the right side. So 4a2 must be equal to 1. Here we have no t term on the right side. So 4a1, that coefficient must be 0. And finally 2a2 plus 4a0 must also be 0. So this is how we match against getting just plain old t squared on the right side. So now, so now what do we get for the values of a0, a1, a2? Some are easier than others.
A2 is 1/4.
Yep, a2 is 1/4.
A1 is 0.
And those are the easiest ones.
And A of 0 is -2.
I think you went the wrong way on something here.
-1/8.
Yeah, minus 1/8. Yeah, so you get
Yeah,
1/2. Yeah. Okay. And with 4a0 is equal to minus 1/2, and then you divide by 4. Okay. Questions about this? All right. So now the undetermined coefficients have been determined. So we can write down the first part of our particular solution, yp1. So that's equal to 1/4 t squared minus 1/8. Okay. Just by putting those coefficients in there. Okay, so now we have part of our particular solution, part that came from the t squared. So now, go back over here and repeat this for the other side, 3e to the t. So I have, I'll call this g2 of t is 3e to the t. So now what we have is we have a constant, 3, so that's a polynomial, whoops, sorry to everybody watching. A constant, so that's p0 of t, a polynomial degree 0 is a constant, times an exponential, where e to the at, where in this case a is equal to 1. So now, the form of a particular solution is going to be some power of t we'll determine in a bit, times a polynomial of degree 0, again a constant, times the same exponential, so it'll be e to the t. So the same exponential that comes in your g. And now s is the number of times that 1 is a root of a characteristic equation, because you have e to the 1 times t. So whatever exponential you have, if it's just an exponential, then the coefficient is what you check against your roots of a characteristic equation. And 1 is not one of those roots. So again, s is equal to 0. So we just have a constant times e to the t. So this is nice. There's only one undetermined coefficient to find for this part. Questions about how we get that form? Okay. So now we'll fill in that form and derivatives for yp2. All right, so the form is a0 e to the t. Well, this works out beautifully because the derivative is just itself. Okay. And we substitute into y double prime plus 4y is equal to 3e to the t. So now I fill in my particular solution and its second derivative for y double prime plus 4y. All right. All right, so in this case, well, I'll erase everything from this point. It's all going to be different. So we don't have powers of t to group by this time. Although, in some cases you might. If we had t to the s where s was non-zero, then it would be a good idea to group by powers of t. So I combine all this, and what I have is, 3e to the t on the right side. And so I have 5a0 e to the t on the left side. So what is a0? Yes, it's 3/5. Now the exponentials on the two sides are all for the same. So you can figure in terms of canceling those and seeing what's left. Okay, so we have 3/5. Therefore, the second part of our particular solution, so yp2 is equal to 3/5 e to the t. Okay. So now we can put the two pieces of our particular solution together. So that's 1/4 t squared minus 1/8. Oops, that went badly. Minus 1/8 plus 3/5 e to the t. So this is a particular solution of the original non-homogeneous problem with both terms of g included. Okay. So now I can get the general solution by adding in the homogeneous solutions. That's c1 cosine 2t plus c2 sine 2t, and then plus, I just add on this particular solution. So 1/4 t squared minus 1/8 plus 3/5. Okay. Where c1 and c2 are found by accounting for the initial conditions. So we need the derivative solution to handle the initial conditions. So we're going to have minus 2 sine 2t plus 2c2 cosine 2t, and then we have plus t over 2 plus 3/5 e to t. So that's our y prime. So now we're going to substitute t equals 0 to get y0. And so when we substitute in t equals 0 into y of t, well, sine of 0 is 0, 1. So we're going to get c1, and then we have 0 from here, and then minus 1/8, and then e to the 0 is 1, so we get 3/5. And that has to be 0, because that's the initial condition. Y0 is 0. All right, so. Similarly, for y prime is 0, we plug in t equals 0, and we get 2c2 from a cosine term. Nothing from here, and then we have, again, plus 3/5. And that is equal to 2, because that's the initial condition for y prime. So now we have fortunately independent of one another. So we can solve the first one to get C1, and the second one to get C2. And what you end up with is C1 turns out to be not a nice number, so minus 19 over 40. And C2 turns out to be 7 over 10. All right, so those are the values that we substituted into C1 and C2 into a general solution, and then you're done. That is your final answer. There's a little more detail for this example, pages 70 and 71 of the notes that I put on the site. Any questions about what you see here? All right, so now what I'm going to do is go back and find a particular solution, show you how it's done using variation of parameters. At least we already have some idea of what we should get. Now, just like in undetermined coefficients, I'm going to proceed one term at a time. Okay. Actually, before I get into that, one thing we'll need is Wronskian. Wronskian of y1, y2. So this should really be the first thing you do for variation of parameters. You have your y1 and y2. You have y1 and y2. We need the Wronskian of them. So that's going to be y1, y2 prime minus y2, y1 prime, where y1 and y2 are cosine 2t and sine 2t respectively. So that's going to be cosine 2t. And then y2 prime is going to be derivative of sine 2t, so that's going to be 2 cosine 2t. And then minus y2, which is sine 2t, times the derivative of cosine 2t. So that's going to be minus 2 sine 2t. All right, so now, if any Wronskian you want to try to simplify as much as you can before proceeding. This actually simplifies a ton. If you remember any of your trig, you'll see what I mean. So, what?
It's 4, right?
Not 4. Close. It does simplify that much. It doesn't. Why does it simplify to a number?
Cosine squared plus sine squared 1.
Yeah. So we have a common factor of 2 we can factor out, and you end up with cosine squared 2t plus sine squared 2t. And all of that, cosine squared plus sine squared of the same angle, whatever it may be, it's always 1. So Wronskian turns out to be 2. Right. Now, so anytime you need a Wronskian for selection for variation parameters problem, if your homogeneous solution is cosine AT and sine AT, from this you can see the Wronskian is always going to be that number A, the coefficient of t in the sine and cosine. So that's one of those time savers if you can remember that. So that's nice because we're about to do integrals, but now we know the denominator is a constant. Okay. Now, so for me, I just realized I think I'm going to regret this example, but I'll plow ahead. For the first term in the right-hand side, t squared. So what we have is the particular solution, which I'll call yp1 like before, is w1 y1 plus w2 y2, where w1 is the integral of minus y2 times g over Wronskian so that's the formula I wrote before. So now if I fill in all that, so y2 is sine 2t, so I have minus sine 2t times the g, which is t squared, all over 2. And then w2 is equal to the integral of y1 g over Wronskian so that's going to be cosine 2t times g1, which is t squared, all over 2. Okay, so those are the integrals that we get. And this is where we find that this problem is one that is best worked out using undetermined coefficients rather than variation of parameters, because what would you get, or what would you need to do to work out these integrals?
Integration by parts.
Yes, and that's bad enough, but because it's t squared, got to carry it out twice. And that's okay because it actually gets even worse after that. Because after dealing with t squared, we move to the other term, 3e to the t. And we, so now we have an integral just like this, except we'd have, for this one, it'd be minus sine of 2t over 2 times e to the t, and then cosine 2t over 2 times e to the t. That is also integration by parts. Now, does anyone have unpleasant memories of doing integration by parts when it's an exponential times a cosine or sine? What nasty thing happens when you do that? Does anyone recall encountering that in Cal 2? Or maybe your Cal 2 instructor wasn't sadistic enough to do that. What happens is, like, you have e to the at cosine bt. So then you do integration by parts. Your next integral is e to the at sine bt. Okay, you do integration by parts again. And you're back to e to the at cosine bt. You're back where you started. Except not entirely because there's a different constant factor, so then you have to rearrange and solve. It's doable. is just an enormous pain. And this is not a Cal 2 class, and I would not put that on a test. So I'll be sure to check whatever variation parameters problem I have, or I'll just let you use undetermined coefficients. Okay. Okay. So, because I also have another example that I want to do, I'm going to cheat in this case. I just use Wolfram alpha to handle the integral. Okay. So what we get for W1 of t, so the integral over there, minus 1/2 sine 2t, t squared. Okay, we get 1/8 times the quantity 2t squared minus 1 times cosine 2t minus 2t sine 2t. And then, working out the other integral, same thing except no minus and there's cosine. Okay. I don't like how it simplifies things, but okay. So, well, similar form, 1/8 2t squared minus 1 sine 2t plus 2t cosine 2t. All right. Now, I'm going to recall from what I did earlier with undetermined coefficients what the particular solution turned out to be. Is 1/4 t squared minus 1/8. You might think, how in the world are you supposed to, from what we have here? Well, we have to keep in mind that the solution is obtained from these by multiplying, so it's W1 Y1 plus W2 Y2. So I have to take the first one, and then the second one multiplied by sine. So now I'm going to get 1/8 2t squared minus 1 cosine 2t squared, because y1 is cosine, minus, I'll distribute the 1/8 through, so minus t over 4 sine 2t cosine 2t. So that's w1, y1. And then we have w2, y2. I multiply the second part by sine 2t. So plus 1/8 2t squared minus 1 sine squared 2t. And then I have plus 2t over 8, so t over 4 cosine 2t sine 2t. And that works out beautifully because the two terms, the second term on each line, those will cancel. And then here we have the same common factor times cosine squared here and sine squared here. cosine squared plus sine squared equals 1. So we get 2t squared over 8, so that's t squared over 4 minus 1/8. Wow, a freaking miracle. So now, undetermined coefficients and variance of parameters, they will not always produce identical particular solutions, but if there's a difference, it's because like maybe it's off by a constant times y1 or a constant times y2. So that's part of a homogeneous solution. So maybe mathematically equivalent in that sense at least. But here, in this case, they turn out to be identical. But yeah, this is variance parameters would be a very messy way to work out this problem. Yeah. Okay. So I have another example here that I think will be more suitable. Okay. All right. Now, any questions about what happened here? Yes.
What happened to the cosine squared of 2t and the sine squared of 2t? Just how did that cancel?
Okay. Common factor.
Yeah.
So I factor that out, and what's left is cosine squared plus sine squared.
Okay.
Other questions? Okay. And then, so these nasty integrals down here, to complete the problem, you would repeat this with, instead of t squared, you'd have 3e to the t. Again, a monstrous integration by parts or Wolfram alpha exercise. And the same result would happen where we get this kind of simplification to terms canceling or cosine squared plus sine squared equals 1 to wind up with the particular solution we got in that case, so 3/5 e to the t. And then everything else would proceed like what I did before. But I want to make sure to do this example. This next problem is one that you cannot use undetermined coefficients. You have to go with variation parameters because it's a problem that does not have constant coefficients. So undetermined coefficients has that limitation. Variation parameters does not. Okay. So this problem is t squared y double prime minus 1 plus t y prime plus y is equal to t squared e to the 2t. Okay, and we're assuming that, I'm not going to specify initial conditions, we are going to assume that t is positive, otherwise, well, you'll see what happens, we're going to end up dividing by 0 otherwise. Now, very first thing you do, make sure that y double prime is by itself. If there's any coefficient, you need to divide by it or you'll throw off everything else. So, get the equation in this form, y double prime minus 1 plus t over t squared y prime plus 1 over t squared y is equal to, 1 over, wait, something's off here. Or something off in my notes. Oh, yes, sorry. T is a coefficient of y double prime, not t squared. Okay. It's going to have t e to the 2t. Sorry about that. Okay, so divide by t, and this is what you get. Because any solution formulas we'll use will depend on that. Okay, now, normally what you would do is find a homogeneous solution. You don't have a method of doing that. I have to give that to you. So a homogeneous solution is equal to constant times y1 plus a constant y2, and y1 of t is equal to 1 plus t, and y2 is equal to e to the t. So those are solutions of this equation where the right-hand side is 0. All right. Now, should be a minus there. Okay. You see, if you plug in e to the t is its own derivative. So y prime, y double prime are all equal to e to the t. And then I would just get 1 plus 1 over t minus quantity 1 plus 1 over t, and I get 0. If I plug in y1 equal to 1 plus t, the second derivative is 0, and the first derivative is 1. So again, I have this nice cancellation. By the way, I said you don't have any method of finding these homogeneous solutions. However, can anyone tell me why I would really only need to give you one of these? Why is only one of them absolutely necessary for you to proceed? How would you get the other one? It's something we've covered. Reduction of order. So if you're given one homogeneous solution, you can use reduction of order to get the other one. Okay. All right, so now what we need, so after our first step, the next step is the Wronskian of y1 and y2. So that's y1, y2 prime minus y2, y1 prime. So we plug in all of this. So y1 is 1 plus t, y2 prime is e to the t, minus y2, e to the t, times y1 prime, which is 1. So we end up with e to the t plus t e to the t minus e to the t, and the e to the t's cancel. So Wronskian just turns out to be t e to the t, so it's not a constant in this case. Okay. So now you go about your particular solution. So P, the particular solution is W1 times Y1 plus W2 Y2. And the formulas for W1, gives, so that's the integral of minus Y2 times G over Wronskian. So when you fill in all those pieces, we get, okay, so y2 is e to the t, and then g is t e to the 2t over the Wronskian, which is t e to the t. Okay. So that works out quite nicely because, as I mentioned before, simplify as much as you can. The t's cancel, and we have an e to the t that cancel above and below. So all that's left is minus the integral of e to the 2t, which is what?
2t over 2.
Yeah, you have to divide by the coefficient of t, so minus 1/2 e to the 2t. Okay. Okay. So now we have that part of a particular solution, so that wasn't so bad. So now we need the other part, W2. So W2 of t is the integral of y1 times g over Vronsky. All right, so y1 is t plus, or 1 plus t. G of t is t e to the 2t, t e to the 2t, over Vronsky, which is t e to the t. Okay. So there's some simplifying that goes on here. The t's cancel. And then e to the 2t over e to the t, you subtract the exponents. And you're left with e to the t. And then the 1 plus t stays. Okay. So this integral not as simple. This one does require integration by parts, but at least it only has to be done once. So if this is the u, and this is the dv, then v is the integral of this, which is just e to the t. And then du is the derivative, get more like a u, derivative of this, which is just 1. So du is equal to dt. So now we apply the integration by parts formula, so that's u times v minus the integral of v du. So that's going to be 1 plus t e to the t minus the integral of v du, but that's just e to the t. So then, working all this out and simplifying as much as we can, 1 plus t e to the t minus e to the t. Distribute, and we get the e to the t's canceling. So we get just plain old t e to the t. So that is our W2. Questions on that? At this point, I can't rule out having integration part by parts exercise of this nature, but not something we have to go through multiple times because that's just evil for an in-class test. Okay, so now we can complete the assembly of the particular solution. So a particular solution, so that's W1, Y1 plus W2, Y2. So W1 was found earlier, that's minus 1/2 e to the 2t times Y1, which is t plus 1, plus W2, which is t e to the t, times Y2, which was e to the t, So we have minus 1/2 e to the 2t, t plus 1, plus t e to the 2t. Okay, let's see. It is possible to condense this a little bit, but not necessary, and I wouldn't want you taking the time to do that on a test either. So to wrap up, the general solution y of t is a constant times y1 plus another constant times y2 plus a particular solution. Where this first part is the homogeneous solution, and then the second part is a particular solution. And if you were given initial conditions, then you would use those to find the values of C1 and C2. Yeah. So actually what I have here to note is this condenses to 1/2 t minus 1 e to the 2t. But again, it doesn't matter, certainly not for a test. This is fine. Okay. All right. So that concludes our methods for solving these kind of higher order equations. So our next class, presumably, we'll see with all this virus situation. When we come back from the spring break, I'll talk about the project, the end of semester group project, which again may have to be adjusted because of the coronavirus situation, but we'll see. And then one more section of this, the week after spring break is all about test 2. So it's coming, but not that quickly. So I'll stick around if you have any questions.